so that connectivity will be better.
Yeah, let me try this. I was asked to do this. How to switch on the camera? And how to go to the next page?
It is not necessary. If your connection is good, it is not necessary.
It is not necessary.
No, it's not necessary, then it's good.
So shall I start, Rajesh?
Yeah, please go ahead.
Okay, thanks for Ravi for inviting me to give a talk here. This is first time I'm giving a talk. I don't know how it is going to come. But I hope it will come like this. So what I'm going to do is topic of optimal control problem. So what is the meaning of that? So you is it the conservation law? We form U3 plus f of t x 2 of x is equal to 0. X belongs to scalar conservation law. The one dimension t is positive. U at x0 is equal to the x. So look for solution of this equation. Okay. And also I'll also can
Adimurthi,
tell me.
I think I at least myself I am not able to hear very well. If you have an Audiphone, maybe it would work better. Probably, if you do you have? I don't know if others hear you well because I seem to have some interference.
Yeah, there is interference because there are two equipments nearby.
Okay. I think
so you just in the laptop you can just mute it and switch off the camera. That's all.
Okay. Now it is fine. Hello?
And lower down the volume in your iPad. In your iPad, lower down the volume.
Yeah. Now it is fine. Hello?
Yeah, much better.
Okay, good. So I'm looking for a weak solution for the equation. Also in the class of weak solutions, I just have the weak solution. That is fine. Fine. Copy the I hope everybody knows about the weak solutions and the entropy condition. So I'll assume this and I'll proceed with it. So what is the control problem? So you are looking for what are the assumptions? To assume that the flux x u into f of t x u.
Prasenjit, I have one more suggestion. Excuse me. Hello. Do the contrary. Actually, still there is an echo. Switch on the mic of computer and mute it and lower down the volume.
But for a timing, I move that to viscous place.
I am not able to listen anything. Hello. Yeah. Now yes. Yeah. Now yes.
Hello.
Yeah. It's much better now.
Hello.
Yeah. Hello. Yes. Now.
Now it is fine.
Yes.
Okay. So no. The assumption is that I'm assuming that the flux, the F is called the flux. The flux has local Lipschitz property with respect to variables x comma u. X comma u. Okay? So they are local Lipschitz values, right? Then this problem as you say unique this problem as unique entropy solution. The idea this is due to Kruzkov. So we always look for entropy solution. We always look for a solution by definition. By definition
I am not getting the sound, not getting the voice.
Hello? Can you hear me now? Hello?
It's too loud. It's too loud. It's too loud. Now it's gone. Hello? Can you listen to me? Hello?
Just a minute. Hello? Can you hear me now?
Yeah, this is much better. Much better and
Okay,
clear.
now it is better. Very good, very good. So the problem is, so u of x denotes the solution for the problem P. Then, so fix a time t, fix a capital time t is positive, and a function h from R to R, a continuous function with compact support. Question is problem R, the problem one. One is that does there exist does there exist this u naught belongs to say L infinity of R, and if u of xt is the corresponding solution of this equation, and u of xt be the solution then says that u of x at the time t is equal to given function h of x. This is called this is called the control problem. Suppose this control problem has no solution. Then you look for the second problem. What is the second problem? Same thing, given a time t and a given function h. Then you look at the associated with u naught. You associate with the cost function. Functional g of u naught defined by g of u naught is equal to integral or r modulus of the function u of x at the time t minus h of x the whole square. The L2, look at the L2 norm of the given function with respect to this. The u of xt denotes the solution with the initial data u naught. Then you minimize this infimum or u naught, g of u naught. Question is that does there exist a w naught such that g of w naught is equal to g of u naught? Okay. This is called optimal control. This is w naught is called the optimal control problem. So question is that whether the control problem or an optimal control problem has a solution or not. Question is whether control or optimal control problem.
Just
has it, yes, tell me.
So, Kate, does it have to be in the full domain, or it can be also
I'm
on
always
some?
assuming that in a full domain. Full domain means
Okay.
real line.
Okay.
I mean, you are given the function h at the point h is at the you are given that h of x at
Yeah.
time t. Now, question
Yeah.
is that does there exist a u naught? And if you denote the u of xt to be the solution for this equation at the time t, which is equal to u of xt, then you call this way our control problem. If it is not possible, can you can you take the L2 norm of that and minimize it? Hello, is it okay?
Yeah, I understood.
Okay.
Thank
So
you.
this
Yeah.
is this problem has been studied so it started by the engineers and studied by the lot of mathematicians in the 80s and 90s, in 60s, especially J.L. Lyons and its school. And then a lot of work is went on for the heat equations, etc., which I'm going to not talk about it. What I'm going to talk about is with respect to the conservation laws. Why the conservation law? The conservation law is completely open. It is the problem is that you cannot use any of the techniques which has been used earlier to study the control problem or the optimal control problem. Therefore, because the linearization or Hilbert uniqueness method will not work here. So that's why I'm going to talk about this one. So first, before basically, I'm interested in knowing what happens if it is a discontinuous. What is the assumption? Assumption is that you assume that xu going to f of t xu is locally Lipschitz. Now, if you drop if you drop the assumption, drop this assumption of local Lipschitzness, say assume that it is discontinuous in the x variable, then the question is how does one prove the existence and uniqueness? How does one prove existence? So regarding these two questions, there are still a lot of open problems. So then, as I proceed, I'll state this one. First, let us assume that to begin with, assume that there are no f is a function of only t xu is purely a function of f of u. The classical problem. Say for example, this one assumption. Second assumption is fu is uniformly convex. That is for example, fu is equal to u square by 2. It turns into the Burgers equation. Now let us discuss first this case, and then we'll come back to the discontinuous situation. So what is this Burgers equation? So let us look at it. So we are interested in ut plus f of ux, and these are the two assumptions we are looking at it. Equal to 0, x belongs to R and t positive. U of xt is equal to u of x0 is equal to u naught of x. So this is the problem Burgers equation. Like f is a uniformly convex, I'm assuming it. So first look at how the solution are obtained. There are two methods. Classical methods. One is vanishing viscosity. That is, you look at ut. Sorry, what is this? Ut. Sorry, vanishing viscosity. Our first method is vanishing viscosity. Second method is Hamilton-Jacobi. I call this Hamilton-Jacobi method. So I'll concentrate on the Hamilton-Jacobi. This works only for dimension n is equal to 1. The x, that is x direction, x dimension, and f is uniformly convex. Is convex or uniform. So let me So I want to solve this one. Let's convert this problem into Hamilton-Jacobi equation. Hamilton-Jacobi, put v of xt. V of xt is equal to integral of u of xt and u of theta t d theta from 0 to x. Then what happens is that dv by dx is equal to u of x t. This is what the because this is what we have to do. So using this, we can convert this problem even into Hamilton-Jacobi equation. What is that? We would love to solve this equation f of xt plus f of dx equal to 0 and v of x0 is equal to v naught of x, where v naught of x is given to equal to 0 to x 2 naught of theta dt. This is the Hamilton-Jacobi equation. So we are not simplifying it. Then u is equal to dv by dx turns out to be the solution for the conservation law. Conservation law. Okay? Conservation law. So how do you solve this? So there is a method to it is basically linear reciprocation. To denote x of t is this where the convex are supremum of pq minus f of q. So q belongs to R. This is a financial dual. Then f double star is equal to f. And using this, we can write down that f of dx is equal to supremum over q belongs to R 2vx minus f of q. Using this, we can write down the solution v of xt not a solution. We can xt is equal to infimum of gamma belongs to gamma of xt. I'll define it. What is this? V of gamma of 0 plus integral. I'll write down this e to this one f star prime of gamma dot theta d theta, where gamma of xt denotes the control curve. I'll just explain it. What is this? At time t, look at any point x comma t. So look at all straight lines with gamma. The gamma belongs to gamma of xt means it is all gamma is a straight line. Gamma is a straight line. Is an affine function. Is an affine function. Affine, and gamma of t is equal to x, and gamma of 0 is equal to x. Look at the infimum over all these things. Then V turns out to be a Lipschitz continuous function, and V satisfies this equation in the viscosity sense, or almost every way. And U is equal to dV by dx exists because this Lipschitz continuous using the Radman's theorem, and U turns out to be the solution to this equation. As a consequence of this, we have the following very important formula called Lax. This is due to Lax and Olenik explicit formula. So what is the Laxolonic explicit formula? The solution u of xt turns out to be given by f star or f prime inverse. I'll write it as f prime inverse because f is convex. This makes sense. X minus y of xt by t, where x going to there exists a function y, so that x going to y of xt is a non-decreasing function. So this is called Laxolonic explicit formula. So if at all, now let us come to the optimal problem. What is the optimal problem here? Optimal control problem is that given given h, does the x is a u naught, so that h of x is equal to u of x comma t. This is what the optimal control problem is. So this is equivalent to saying that f prime of h of x turns out to be equal to f prime of u of xt, which is turns out to be equal to x minus y of xt by capital T. So as a consequence of this, y of xt turns out to be equal to x minus t times f prime of hx. Now by Lax formula, you just look at it. There exists a non-decreasing function by satisfying this one, and by if at all you want to solve this equation, that means that this must necessarily be a non-decreasing function. This must necessarily be a what is this? This must necessarily be a non-decreasing function. So this is an extra condition which you have to impose in order to solve this optimal control problem. So this is where the constraint come into picture. What is this? I'm not able to get it. What is this?
question is, how do you go back? It is not. It is erasing it. Just a minute. Oh, okay. This is a constraint, and hence optimal control problem in general has no solution. I'm sorry. Now, hence control problem has no solution. So, in view of this, one has to look for optimal control. So this was first started by Zuazua.
Adimurthi?
Yes, tell me. Can you hear me?
Yeah, I didn't understand the conclusion. So you have this explicit formula
Because, yes,
given
yes.
the function at time capital T.
Exactly.
So you know the solution.
Right.
So what does that imply?
No,
that
suppose the optimal. Sorry, it is a control problem. Suppose the control problem has a solution hx is equal to u of xt for some u naught. Let u naught. Suppose there exists a u naught, and uxt denotes the solution corresponding to this initial data u naught, such that at time t is equal to t, u of x is constant with h of x.
Yes.
Then, because the Laxolonic formula says that if this is the case, then f prime of h of x is equal to, just look at it, Lax formula. Then it becomes f prime of u of x, which is equal to x minus y of xt by t. Therefore, y of x you can solve it by y of x is equal to x minus t times f prime of hx. Now, Lax formula says this is a non-decreasing function. That means that necessarily this function must necessarily be a non-decreasing function, x minus t times f prime of hx. Therefore, not all functions have you cannot get a solution. If at all the solution exists, this is a constraint it must satisfy. So therefore, the control problem in general, control problem in general has no solution. Therefore, you look for optimal control. Okay, so this was first looked at by Zuazua and his collaborators, Zuazua and Castro. So what they look at is that they look at all functions from over R, u of xt for Burger's equation, f of u is equal to u square by 2. They look at it u of xt, capital T, t is given, t is positive given, u of xt minus h of x whole square dx. Now minimize this, infimum over u naught belongs to L into T is compact support, assume that H has compact support. Now, what they show is that they show that there exists a u naught, so that this infimum is actually equal to G of u naught. Therefore, existence and optimal control is guaranteed. It is not difficult to show that it is optimal control. Okay, existence and optimal control. Now, the question is that it is not existence; it is capturing. How do you capture this optimal control? And like in general, optimal control has many solutions. There are many u naughts which minimizes this functional. Therefore, first of all, the solution is not unique. Second one is that the functional u naught going to integral of mod u of x t, capital T minus h of x the whole square dx is not convex. Therefore, it is not convex, and the solution is not unique. Therefore, you cannot apply the method of descent to capture the optimal control. Therefore, method of descent will not work. Method of descent will not work. So, in order to overcome this difficulties, Zuazua and et al. Consider they propose a scheme called, I'm not going to talk much about it, called descent. What is it? Descent algorithm. it is close to descent algorithm. To capture this solution, capture one of the optimal controls. It is just a scheme. So now the question is that whether really this scheme really converges the optimal solution, because the solution admits shocks and the rarefactions. Okay, therefore, whether this is really gives the optimal solution, and the convergence of this scheme, and the convergence of this. So this is a big open problem. Even today, it is big. Nobody has solved it. Big open problem. Okay. So what we looked at is that instead of looking at this one, you look at we have a different answer. We consider this problem in a different angle. Where optimal solution exists and computable using the computer. So this is what I'm going to talk about for another few minutes, and then I'll shift to the discontinuous effect, because this is important. How do you do that? So look at the cost functional. What is this? You want to look at u of xt minus the h of x whole square dx. Assume that, for example, f of u is equal to u. Doesn't matter. U square by 2. Therefore, f prime of u is equal to just u. It is a okay. F prime of u is equal to this. You look at it as a functional. Now use this one can be. Now assume that u of xt given u of xt is coming from the initial data u naught of x. So by Laxolonic formula, this can be converted into integral of u naught of x minus y of xt by half Lax formula minus h of x the whole square dx by Laxolonic explicit formula. Now this can equal to 1 by t square integral minus into plus infinity modulus of y of xt minus x plus t times h of x the whole square dx. This is just this one. Now I want to minimize. Instead of minimizing u naught, you minimize your y. So what y? Y is equal to, look at all functions y, it's from R to R. Y is a non-decreasing function, and y is the integral. Say y of yx minus x belongs to L2 of R. So this is a closed convex set. It is a closed convex set in L2 of R, and the functional I, call this I, then I turns out to be the projection. I turns out to be the projection. Finding the minimum is the same thing as minimum of minimum of I of u naught, I of y naught. Let us call this y. I of y belongs to k is nothing but a projection on the convex set. Convex set x, which is a convex set k, which is a linear problem. Okay, this is well understood. Because L2 is a Hilbert space, k is a convex set. Therefore, you can always have a projection on this one. Therefore, existence of y is well defined. X is therefore. Oh, no. You go about, how do you? Existence of y is well defined, is well known or well defined. So that is not a problem. Now given y, now the question is that if you want to solve this optimal control problem, what you have to show, given y, does there exist? You say u naught says that the solution u of xt turns out to be equal to the f prime inverse of x minus y of x by 2. This is the question. Suppose you do that, then we are through. So this is what is called, what is known as a backward construction. Backward construction. I'll explain this in a moment. Backward construction. So for the time being, assume to explain this one, assume that there exists an m1 less than m2, so that yx is equal to x if x does not belong to the interval m1 and m2, and some constant a if x belongs to m1 and m2. That is what I mean by that is yx is not decreasing function. So m1 is here, m2 is here, m1 and m2 is here. Yeah, a is somewhere here. So up to this one it is x. Here up to this is x, and it is a here and a here. There is a point of discontinuity at this point. Right? Y. Okay. Is it clear? Yes or no? So this is something like this. It comes up to m1 and m2. So this is my y. So now I want to now use the I want to construct that u naught says that the solution u of xt corresponding to this u naught turns out to be f star of x minus yx by t. How do you do that? So it is this is what I call this a backward construction. Backward construction. So what you do is that I'll explain that. So this is by m1, this is m2. So now you draw the straight line. This is the time t. This is the time t is equal to 0. This is the time t is equal to capital T. This is my point. This is my point A. So I have got that this is a yx is equal to ax here, yx is equal to x here, yx is equal to x here for x less than m1 or x greater than m1. So you draw these two straight lines. Join them here. Join them here. Now what you do? This is also m1 t. This is m2 t. Okay. So now what you do is that here I'm going to put a rarefaction here. So that is f prime inverse of f prime. I'll write down. F prime, this is a rarefaction, x minus a by t. This is a rarefaction here. I'm going to put it. I'm going to put a shock here. I'm going to put a shock here. So here up to that is equal to u is 0 here. Yx is equal to x, u is equal to 0. U is 0 here. U is this value. This value I call this u1, this is constant. This value I call this u2, and this is equal to 0 here, 0 here, and we can easily see that. This u and here u naught is equal to the same thing because u1 0 here, u2 0 here. This is the data. This is the see that u naught is this data. With respect to this data, this turns out to be the solution for which satisfies this equation. This is called the backward construction. I would like to explain this instead of this one A. I'll explain it in two things. Now what you do is that's the second one. So what you do is that suppose y is given by this. There is a m1 here, m2 here. There's a is here, b is here. So now what you do is that to look at some alpha. If you join this by this one, some alpha, this some alpha. I'm going to now what you do is that here you put a rarefaction. Here also you put a rarefaction. That is f prime inverse of x minus a by t. This is the rarefaction. F prime inverse x minus b by t. This is the rarefaction. So here you can put a shock. You can put a shock here. And you can construct there's say U1, U2, U3, U4, U5, sorry, U0, where U0, sorry, not U0, U1, U2, U3, U4, U5, U6, where U6 is equal to 0. You say U1 is equal to 0, this is 0. U2, we can, U2 is equal to the value of F prime on this line, M1t and M2t. And you can see that this actually gives rise to the, this is put U1, 0, U2, U3, U4, U5, U6, 0. So with respect to this data, you'll get a function y, and it satisfies that u of x comma t for this data, it turns out to be equal to f prime inverse of x minus yx by t. Therefore, you have solved this given y. You have solved this given y. There exists a u satisfying this equation. So this is called the backward construction. For a general y, for y of x is increasing, and y is equal to x outside the interval m1 and m2. What you do? You discretize it, and for each discretization you can construct a data, and then you get a solution. And now main idea is to show that this discretization converges to yx, and therefore the solution must necessarily converge to y. That requires some amount of work. Let us pause on that. This can be done. So this is what you do it for the optimal control problem in the say in the Burgers equation, for example. You can have the complete solution, unlike in Zuazua et al., where it is completely open problem how the convergence of the numerical looks like. Whereas here you can by hand you can construct the inverse problem. It basically our optimal control problem. Okay, this is what it happens in the case of. Just a minute. Okay. So this one has okay. So this is what happens in the case of conservation law. Okay. The case of conservation law. Law ut plus f of ux equal to 0. Next question is consider the case where xu going to f of pxu is not Lipschitz, not locally Lipschitz. So this is a big challenging problem. So even the simplest one is that assume that f of txu, assume that txu is equal to just a function of x comma u, it is space and variable. And what is the simplest one you can look for? There is a one jump discontinuity at the point x. So simplest the flux f of xu is given by f of xu is equal to, say, simplest one, f of xu is equal to hx, the Heaviside function, into f of u plus 1 minus the Heaviside function hx into g of u. That is equal to, basically it is equal to f of u for x positive and g of u for x negative. Assume that f and g are convex, f and g are uniform. So if that is the situation, so I am looking for the solution of the weak solution of this equation, dt of u plus dx of f of xu equal to 0. Weak solution, it's u of x0 is equal to u naught x. This is coupled. This reduces to two equations, namely ut plus f of u equal to 0 for x positive and t positive, and ut plus g of ux equal to 0 for x negative and t positive, and with the initial condition u of x0 equal to u naught of x. And because the interface there is a jump discontinuity on the time t and the time x is equal to 0. This is the t axis, this is x axis. This is I'm looking for two equations: 2 ut plus g of ux equal to 0, ut plus f of ux equal to 0. Then because it is jump discontinuity, so they must satisfy what is known as the jump condition or Rankine condition across interface x is equal to 0. This is called interface. Therefore, across x is equal to 0, called the interface. It must satisfy another equation. Therefore, assume that the right limit u of 0 plus and t exists, and the left limit u of 0 minus t exists. These are assumptions. That the left limit and the right limit must be the flux of the left limit, right limit is equal to the flux acting on the flux at the left limit. This holds. Then you say that the solution is a. Then you say that it is a. Then you solve the discontinuous solution, a discontinuous conservation law with fluxes Fu and Gu on the left side and right side with simple discontinuity at x is equal to the interface. So why it is important? Why one has to look at it? Of course, from the mathematical point of view, this is the simplest discontinuity you can look for. So even otherwise, it has got a lot of importance in the sense that such problems are considered already by engineers called in oil industry, where to extract the oil from the earth. Okay, so and they devise a scheme which is called the where they devise a scheme, numerical scheme, and it worked very well with them to extract the oil from the earth. But the convergence of the scheme was completely unknown, and people are trying to use this hx by the regularizing technique, h epsilon of x. That is, you have hx is like this, so you regularize it. H epsilon, and look at the considering this one a regularized solution, something like u epsilon plus u epsilon of t plus f epsilon of xu of x equal to xu epsilon of x equal to 0. This has always a solution where h is replaced by h epsilon of x. This is transferred with locally Lipschitz continuous. So solution exists, and you basically want to show that what happens to u epsilon as epsilon tends to 0. Whether it converges solution considered by the oil industry people, and unfortunately it is not true. So therefore, what is the solution which you have to look for? So question is, first of all, question is existence of solution. Second one is uniqueness. Third one is that half Laxolonic type, Laxolonic type conditions are explicit formula. The fourth one is that then you look for control and optimal control. Okay, so let me give the answer. This is joint work with myself plus one of my colleagues, Shampoo. So just a matter, we solved this problem some 6 years back, and there's a big gap, and finally that gap was filled, and now it is going to get published. It is not yet come. I'll give the references at the end of the talk. So now let us talk about the existence solution. This is a joint work with myself. Okay. So let me first explain this existence of a solution. What you do is, I'll not going to this one. You convert this into a Hamilton-Jacobi. Convert this discontinuous flux conservation law into Hamilton-Jacobi discontinuous Hamilton-Jacobi. In the sense that ut plus et plus f of vx equal to 0 for x positive and t positive, vt plus g of vx equal to 0 for x negative and t negative, and V of x0 equal to V naught of x, which is the same thing as the primitive of the u naught of theta d theta. This is given. So you are looking for a solution. You are looking for a solution. You are looking for a solution of this equation. So how do you get this solution? So again, we can use the, because f and g are convex, we can use the convex analysis to write down the solution. Let me write down the solution. So what do you mean by solution? I'll explain it in a moment. Define v of xt. This is the v of xt. They call the value function. Define the value function. Function v by as follows. Infimum over gamma belongs to gamma of xt. I'll define what it is about. V naught of gamma of 0. This is given. Let's look at all gamma which is positive. Look at f prime inverse of gamma dot theta. Sorry. Yeah, f star d theta plus for all gamma on the set where g prime inverse of gamma dot theta is a derivative of gamma theta, Lipschitz continuous functions, plus on the set where measure of set theta says that gamma of theta equal to 0, this measure of set into minimum of f star 0. So let me explain this one. So okay, if you look at this as the v of x is defined like this, then you can show that v is a Lipschitz continuous function and v satisfies this almost everywhere, and v is Lipschitz. Okay, v is Lipschitz. You can show that v is Lipschitz, and v is a solution almost everywhere to Hamilton discontinuous Hamilton Jacobi. So this is very important. V is Lipschitz continuous. So now I would like to explain what is the gamma is. Gamma is instead of writing it down, I'll write down what it is. Gamma is I'm going to write down. So what you do is that this is time t. This is a t-axis. Look at the t-axis. Look at the xt. X comma t. Now look at all curves so that first of all I want to say gamma of t must be equal. Gamma is a mapping from 0t to r. Lipschitz continuous. Okay, Lipschitz function satisfying the property that a gamma of t is equal to x. So now I'm not going to take about all gamma. Either it is a straight line, or it is a straight line comes here and bends over here, or it comes and here and comes here and this one. It slides and reflects back. Therefore, you call it gamma 1, or gamma 1 and gamma 3, or gamma 1, gamma 2 and gamma 3. So similarly, for if x lies here, similarly you can calculate. Therefore, gamma consists of 3 pieces. Gamma is consists of gamma 1, gamma 2 and gamma 3. Each gamma 1, gamma 2, gamma 3 are straight lines or affine lines, and they must satisfy this property. Okay? Such a curve is called the controlled curve, and collection of all such curves is denoted by gamma of x. All curves and take the infimum over all these control curves, and what happens is here minimum of theta. So that means only this portion will come. This is the portion where gamma 2 is equal to 0, gamma of 2 theta is equal to 0. So look at it, all theta says that gamma of 2 theta is equal to 0. Take the measure of that. This is equal to, say, if it is T2 and T3, this is equal to T2 minus T3. What is the f star 0? F star 0 is nothing but minus f of theta f minus g of theta g, where theta f and theta g are denoted the minimum of f and g, because I'm assuming to this one. Therefore, it is a constant. So if you look at infimum over all these things, you get a solution. You get a function we call v of xt, and minimizers are called the characteristics, and v of x is satisfies the discontinuous flux function, discontinuous Hamilton Jacobi equation, and the derivative dv by dx really is equal to u of x. If you define that, then u turns out to be the solution for the discontinuous conservation law. This is how you can get the solution for discontinuous algebra. Now we will talk about the Laxolonic type formula. Look at the Laxolonic type formula. Laxolonic type formula. Because this plays an important role in control and optimal control problems for the and the conservation laws. What is the Laxolonic type formula? In the earlier case, we saw that u of xt or f prime of u of xt at any time t is equal to, there exists a non-decreasing function of y of xt, such that this is given by, the solution is given by where u satisfies ut plus f of ux equal to 0. Now I am looking at, instead of this one, I am looking at ut plus f of ux equal to 0 for x positive, ut plus v of ux equal to 0 for x negative, with the initial condition u of x0 equal to u naught of x. So how do you get the similar Laxolonic type formula? So in order to get this Laxolonic type formula, first let me just a minute. Okay, and if another 5 minutes is there, I'll explain it. No, I'm not. I'll just explain this Laxolonic type formula. So, okay. So what you do is that, what is the Laxolonic type formula? So I wanted to do the Riemann problem, but let us not bother about it. So let me explain the Laxolonic type formula. So what is the Laxolonic type formula? This is the one. Oh, shit. So at any time t, I want to find the interface t. Assume that, for example, f of theta f is less than equal to g of theta g. That is, I'm looking at my fluxes are like this. F is like this and g is like this. This is f, this is g. This is equal to theta g, the minimum of f g. Theta g equals to g. This is the maximum minimum of this theta f. It has intersects at 2 points. I denote with theta g bar. This side intersects with theta g double. This is the notation I'm using it. So you can find a Lipschitz continuum. I'm assuming that assume that there exists R1t, R2t, the Lipschitz continuous function with respect to the t variable. So, and there is an L1t. So that for t, for this is x-axis, this is 0. So I would like to explain this. If use the u naught is the initial data and u of x is the solution to the discontinuous. Yes, tell me. U of x is the solution. So how do you get it? Then you can show that the RT is a curve. It comes at the point t naught. You can write down this one. This is the point psi naught. You can write down the solution f prime of theta g bar. So not really. The solution becomes. I'm describing it. So this is the straight line. This is the straight line. The slope of this straight line is equal to f prime of theta g bar. Okay, this is the parallel to this. So in this portion, the u is equal to theta g bar. There is a something like this. Here you will get the standard Laxolonic. There is a non-decreasing function y of x, standard Laxolonic formula. Get it? Here also standard Laxolonic formula. You will get it. So and here you get a sort of a rarefaction. Sort of a rare. This is what the you can describe how the solution looks like. So this is what I call Laxolonic type formula. Laxolonic type formula. So it is you can describe it mathematically, but it is easy to explain it in a pictorial way. So once you describe this in this one, therefore, if at all the control problem has a solution, this R1t or it must necessarily satisfy this type of Laxolonic type of condition must be satisfied. So if the Laxolonic type of condition is satisfied, that means that you are given that L1t, R2t, R1t are given. So and also there is a y naught, y at t is given. Sir, y of x is given. It satisfies the following. I mean, what I want to say is that is given u naught. There is a solution u of xt is given. For this u of xt, it generates the 5 quantities L1t, R2t, R1t, y of x. Therefore, thing. So satisfied. Either L1t is always less equal to 0, R1t is always less equal to 2, and 0 less equal to R2t, less equal to R1t. This is first hypothesis satisfied. Then L1t equal to 0 implies that L1t is strictly negative implies R1t is positive equal to 0, or L1t equal to 0. R1t is strictly positive implies that L1t equal to 0. These are the two conditions. Third condition is y is defined from minus infinity to R2t. Union R1t to infinity to R is a y of x going to y of x, x going to y of x is a increasing function. Non-decreasing function. And then using this one, you can define Laxolonic type. Laxolonic type. So because of lack of time, let me cut it short. I'll tell you what is the control problem has some conditions. These are all the quantities which earlier in the single flux only yx is given. Okay, this is single flux 2t plus f of ux equal to 0. In the case of the discontinuous flux, you have got 5 values L1, R2, R1, and y. There are 5 values are given. So naturally, if at all the function h of x has an controlled solution, it must necessarily satisfy this constraint. Yeah, that is given by L1, R2, R1, and y. Unlike in the case of the single conservation law, only one constraint is there. Here got 5 constraints are there. So given that 5 constraints, can you obtain then backward? You look for the backward construction. That is what is that? Given that is given 5 values L1, R2, R1, y. Construct a data u naught belongs to L into T of R. Construct, this is construct. So that the u of xt, the solution obtained from the Hamilton-Jacobi equation, gives rise to this L1, R2, R1, and y. This is what the control problem is there, and the backward construction exists. Using this, we can talk about the optimal control. Okay, so because of the shortage of time, let me give this how the backward construction works. Okay, that is the backward construction. This is very important. The backward construction. Backward construction. Okay, so that is we know that L1 equal to 0 if R1 is positive. So without loss of generality, assume that R1t is positive, 0 less than R2, t less than R1t, and y is given. But why not all y satisfied? It must satisfy some compatible condition. I'll explain it in there. So what you do is that you have got R2t, R2, capital T. Here you get R1t given. These are all given. So what you do is that you draw the straight line whose which is parallel to the 2 parallel lines, and the slope of the inverse of the slope is equal to f prime of theta g bar. Similarly, it is f prime of theta g. Now you can always find, there always exists, because of this, you can always find the tau naught and the xi naught, so that this straight line given by, what is that? It must possible that there exists a tau naught f prime of theta g double bar, which I already defined, into t minus tau naught. It passes through the point with the negative slope. This is what, and it meets the x-axis at xi naught. So this y naught is somewhere here. Y naught of R1 of t is somewhere here. Okay. Now, so now what you do is that you have this figure. Let me write down that. Therefore, I'll make it. I'll make it a much bigger figure. So you understand what it is. Therefore, what you do is that you've got R2t, is R1t. There is a here. Then you join this by this. This is a this is the xi naught given R1, R2, and R1. You can always find a tau naught. And y naught is given. Y naught is somewhere. Y naught somewhere like this. This is the value of this one. This is y naught of xt. Y naught of x, you get it here. Y naught of x, you get it. So what you do is that you draw a join this by this. There x is a curve joining this on this one, and here below that you will get a rarefaction. This is backward construction. What is this is given? I am constructing a solution. How do you construct the solution? The solution is in this region. Define u is equal to theta g. It is every constant is a solution. You get theta g part. Here it is given by f prime inverse of x minus xi naught by t, and you put a shock curve so that to the left of it is equal to theta g bar, to the right of it is equal to f prime in this one. Here you put u is equal to theta g bar. Here theta g double bar. Sorry, theta g double bar. Now what happens is that here I can there exists y naught here, because y naught is defined from here 0 to R2 and from R1 to infinity. Therefore, it looks like this. So here you put Laxolonic, standard Laxolonic, backward construction. Here also is the standard Laxolonic backward construction. Here you put theta g bar. So the problem comes here. It is a rarefaction. Here you put a shock here. Here you put a shock here. Here you put a shock here. So this value and this value, and finally, and here I can put because there's one thing I wanted to tell. It is not a discontinuous flux is not a function. Is not consists of two boundary value problems. The boundary value problem. Just before I want to make a remark. The discontinuous flux is not two boundary value problem. What I mean by that, you solve one here and patch it up. Because if that is the case, each, for example, boundary value problem, you can have a rarefaction from the boundary, which is not the case. This is what you in the backward construction. First, you prove that there are no rarefactions on the boundary. So, in view of it, you can always fill up this portion by a solution. This is theta g bar. This is the rarefaction. This is a shock, and this is Laxolonic. This is Laxolonic solution. And finally, the backward construction is obtained. Using backward construction, you can formulate the optimal control problem, which for optimal control problem as a solution, and using the discretizing that solution R2, R1, etc. You can use the backward construction to construct the data, discrete data, and show that the discrete data converges to a L infinity data, and everything converges. That is some analysis has to be done. So once you do that, then the control has a constraint, and optimal control problem has a solution which can be computable. So this is what I wanted to talk about in this talk, and I would like to give the reference for this one. It is to appear. This is to appear in communications in contemporary mathematics. This is the communications in contemporary. It is in archives. Okay, so this is exact and optimal control. Control for scalar with discontinuous flux. Okay, so this is what I wanted to talk about. Is it fine? Okay. I think
Thank you. Thank you.
Okay, I'll stop at this stage and yes, fine. So,
thank you, Adimurthi. Thank you.
Okay, thank you. Okay, fine.
Yeah. So let's go for very quick comments and commentary, very fast because we are so late.
Yeah, because of the iPad, I'm not used to this iPad. First time
nobody used to, nobody used to, but the situation makes us to.
Is different from iPad presentation.
Sure, it's much more comfortable. Yeah. Exactly. So very quickly, somebody, please.
I just have a comment on.
Yeah.
So I think
Rajesh,
probably.
Please.
I think talking about the discontinuous flux, and at the same time the continuous, it takes time. So maybe you could have. I mean, you actually merited like maybe 2 talks for.
Yeah, I know that, but without explaining like a continuous case, it is very difficult to explain the discontinuous case.
Yeah. So I don't know, maybe.
Because then very few people are working in discontinuous flux. There are a lot of papers are there in even for Burger's equation.
Yeah. No, I mean, I found it extremely interesting, but I think I will look at your preprint and then, and if there is a chance to hear you again, I will probably again. Yeah.
So the paper is going to appear in this journal maybe next month or so.
Yeah. Okay. Thank you.
Okay.
Nice. Anybody else? Quickly, just one more comment. Very fast.
I have a query. I mean, can I ask?
Yeah. Please.
Yeah, actually, this is Pratima from my IT partner. So, regarding this discontinuous flux as well as this discontinuous initial condition, when I'm going for the numerical approximation, how do I be able to discretize this so that I can get more?
No, I think there are methods called Godunov type algorithms or Lax and not Lax and Of course, anyhow, let us look at the Godunov type algorithm. You know what a Godunov algorithm for the normal conservation law? Hello?
Yeah, at the point of discontinuity, it will not be having enough smoothness, right? So
exactly. Therefore, but Godunov scheme is the best scheme, right?
But if you're only checking in the one-sided part of because for example, suppose at the point x equal to d, it is having a discontinuity. You're taking
you really don't see the discontinuity in the Godunov type. So Godunov, you discretize it. So you'll get the un plus 1, un plus 1 j, right? So that is this is un j. The ijth cell, un plus 1 j is equal to un j plus lambda times f of x un j minus 1 3-point scheme un j plus 1. So you'll get that f of un j minus 1 un j is the Godunov flux minus f of un j plus 1. Right? This is a Godunov scheme for the conservation law ut plus f of ux equal to, right? So this is the, and lambda is equal to delta x by delta t. Is it okay? And f of g is the Godunov function, f of g of ab AB is equal to max or min, depending on max or min, depending on A is f of theta, either A less than B or A greater than B, right? This is the Godunov's flux. So this is the Godunov scheme, and you really don't see the discontinuities. If you are going for a higher order schemes, then the discontinuity plays a role. Hello?
But I'm talking about the error analysis. I mean, for example, when I'm going for the truncation error analysis, at that time, at the point of discontinuity, you are not doing anything. Only in a neighborhood of that, you are only doing the error analysis.
No, if you go for higher order schemes, then the discontinuity plays a important role. So in the case of the discontinuous flux, everywhere it is a standard Godunov scheme here to left. Only the changes in the neighborhood of this interface, where using the discontinuous Godunov. I think there are many papers. You can have a look at it. There are some look into the Maxinet, and there are many papers in this direction. Okay, you can look at any of these papers. Hello.
I can hear you.
I mean, basically the discontinuity comes on the interface, and how to overcome this, it is that. But there are many problems are still open. The convergence of the scheme is completely open. It converges, subsequence converges, but full sequence convergence is completely open, unlike, because there is no entropy condition, or there is nothing, nothing, something like Kruzkov entropy condition does not, not a proved. Not a true.
Convergence not at the point of discontinuity or not at the place of the discontinuity, but in a neighborhood of that you're talking about.
Yes, no. At the point there are things. One is exactly at the interface. You can have the Godunov type scheme, or in the neighborhood of this one also you can talk about. Then you can have the Laxative scheme. In that case, you have to go for the neighborhood. And if you want to have the higher order schemes, then that is completely a different story. Nothing is. Okay.
So we assume that we have enough smoothness in the neighborhood of that, because we are working in L2, but still.
No, you don't have a smoothness at all, because of it is the interface is a point of discontinuity, basically. I didn't show the Riemann problems. You can see that how the discontinuities appear. You can have many papers in this discretization. For discontinuous flux. So, Navier school has done a lot of work. They have done a lot of work on this one. You can have a look at it. Okay.
Oh.
Hello.
Sorry.
Any question?
No.
Okay.
Okay, so if it is done, then sir, let's stop here because we are very, very late now.
Exactly.
Okay, maybe Rajesh is talking in 1 hour and 50 minutes. So we have to go back to that.
It's
back to back talk.
Local
so,
meeting.
what is the time there?
It's 1:15. 1:15.
It's 1:15.
Here it is already 11 o'clock. During 11.
Yeah.
Okay. yeah.
Okay. Okay then.
So everybody from India. Good night.
Good night.
See you next time.
See you. Thank you very much. Bye.
Thanks to you.
Okay,
nice
bye.
talk. Thank you. See you. Bye-bye. Bye-bye, everybody. Bye-bye.
Bye. How to close it?
It was muted in this machine. That is why he was not getting the sound.
What is that? Muted, huh?
Yes.
Oh, that's why you are controlling it, huh?
No, I'm not controlling. The thing was that when